Welcome to the next class on the course on linear algebra for data science. Today we are going to learn about linear independence, basis and dimension. First of all, let us see what a linear combination of vectors is. So suppose we have a vector u in a vector space V, then this vector is said to be a linear of other vectors if u can be written as a sum of scalar multiples of these vectors. That is, u is said to be a linear combination of the vectors v1, v2, etc. vn if there exist scalars c1, c2, etc. cn such that u can be written as u is equal to c1 v1 plus c2 v2 plus etc. plus cn vn. Let us see an example. Determine whether u is equal to 1, 2, 3 can be expressed as a linear combination of v1, v2, v3 given as follows. So, we can say that this vector u is a linear combination of these vectors v1, v2 and v3 if there exist scalars d1, d2 and d3 such that u is equal to d1, v1 plus d2, v2 plus d3, v3. So our aim is to check whether there exist scalars d1, d2 and d3 of this form. Let us see. So we seek scalars d1, d2 and d3 that satisfy the equation u is 1, 2, 3 is equal to d1 times 1, 1, 1 plus d2 times 2, 4, 0 plus d3 times 0, 0, 1. So on simplifying, we see that 1, 2, 3 is equal to d1 plus 2 d2 plus 0 d3, d1 plus 4 d2 plus 0 d3 and d1 plus 0 d2 plus d3. Now, if I am considering this, I can write it as 1 is equal to d1 plus 2 d2, 2 is equal to d1 plus 4 d2 and 3 is equal to d1 plus d3. Now this has become a system of equations of this form. Now using Gaussian elimination method, we can actually solve this equation. So you can actually consider the matrix form 1, 2, augmented matrix if I am considering 1, 2, 1. This will be 1, 4, 2 and 1, 1, 3. So on simplifying and solving, we find that the only solution to this system is d1 is equal to 0, d2 is equal to 1 by 2 and d3 equal to 3. So this implies that there exist scalars d1 equal to 0, d2 equal to 1 by 2 and d3 is equal to 3 such that u is equal to 0 times v1 plus 1 by 2 times v2 plus 3 times v3. That is 1, 2, 3 is actually a linear combination of 1, 1, 1, 2, 4, 0 and 0, 0, 1 as this. 1, 2, 3 is equal to 0 into 1, 1, 1 plus 1 by 2 times 1, 2, 4, 0 plus 3 times 0, 0, 1. Okay, so therefore you can be expressed as a linear combination of v1, v2 and v3. Now, this u is equal to 1, 2, 3 is a particular linear combination of v1, v2 and v3 where the coefficient of v1 must be 0, the coefficient of v2 must be 1 by 2 and the coefficient of v3 must be 3. What if we consider all such linear combinations? That is 1, 2, 3 is just a single combination of v1, v2 and v3. What if we are considering all the set of all linear combinations of v1, v2 and v3? Such a set is called the span of the vectors v1, v2 and v3. That is what we are going to see next. Before that, okay, we have one more example here. Determine whether u is equal to minus 1, 0, 2, 4 is a linear combination of v1 equal to 1, 1, 2, 2 and v2 is equal to 3, 2, 3, 5. So again, we try to find scalars d1 and d2 such that u is equal to d1 v1 plus d2 v2. Now, again on simplifying, what will we get? Minus 1, 0, 2, 4 is equal to d1 plus 3 d2, d1 plus 2 d2, 2d1 plus 3d2 and 2d1 plus 5d2. So what does this imply? This implies that d1 plus 3d2 is equal to minus 1. d1 plus 2d2 is equal to 0. 2d1 plus 3d2 is equal to 2, and 2d1 plus 5d2 is equal to 4. So this has again become a system of equations which can easily be solved. Now using Gaussian elimination, we find that if I am simplifying it, if I am finding the augmented matrix and using Gaussian elimination method to solve it, we can see that this system has no solution. What does that mean? There exists no d1 and d2 such that d1 v1 plus d2 v2 gives u. So u cannot be written as a linear combination of v1 and v2. Okay, so we know how to solve this system. So we will write the augmented matrix as 1 3 minus 1 1 2 0 2 3 2 and 2 5 4. This is the augmented matrix, and by using row reduction you can easily solve the system. And on simplifying the system or converting it to its row echelon form, we can see that this system has no solution. So we cannot find a d1 and d2 such that u is equal to d1 v1 plus d2 v2. Okay, now we'll move on to the definition which we have already discussed, that is span of a set of vectors. So in the first example we have seen here, we see that u actually is 0 times v1 plus 1 by 2 times v2 plus 3 times v3. What if I am considering all the combinations d1 v1 plus d2 v2 plus d3 v3, where d1 d2 and d3 can vary among all the real numbers? Then we will get a set called a span. So a span of a set S is a set of all linear combinations of S. We will see the definition. The set of all linear combinations of a finite set of vectors S equal to Z v1, v2, etc. vn is called the span of S, denoted as span of Z v1, v2, etc. vn, or simply span of S. We have a theorem based on it. The span of a set of vectors, it will obviously be, so v1, v2, etc. vn, say and they are the elements of a vector space V. Then the set of all linear combinations will be a subset of V, and in particular we can say that it is a subspace of V. Because even if we take any two vectors in the span of S, their sum will be in that set and their scalar multiple will also be in that set. So the span of a set of vectors actually forms a subspace of the actual vector space V. Now moving on, we see the definition of linear independence. What do you mean by linear independence? So first of all, we will see what linearly dependent vectors are. A set of vectors v1, v2, etc. vn in a vector space V is linearly dependent if there exist scalars c1, c2, etc. cn, not all zeros, such that c1 v1 plus c2 v2 plus etc. plus cn vn is equal to 0. I'll give you an example. Suppose we consider two vectors 1, 1 and -3 in R2. Suppose I am considering C1, this is my V1 and this is my V2. Now suppose I am considering C1 V1 plus C2 V2 is equal to 0. This is the equation I have to consider. Then C1 times 1 1 plus C2 times -3 must be equal to 0, which implies C1 minus 3 C2 is equal to 0. On just simplification, we will see C1 minus 3 C2 is equal to 0. This means that both the equations are just the same. So if I am considering just one equation, I get that C1 is equal to 3 C2. So C1, the only restriction is for C1. C1 must be equal to 3 C2. So C1 and C2 can be like this, 3 C2 and C2. That is, If I am giving C2 is equal to 0, C1 equal to 0, C2 equal to 0 is a solution for this system. If I am giving C2 is equal to 1, C1 is equal to 3 into 1, 3, and C2 is equal to 1 is the solution for the system. If I am giving C2 is equal to 2, what will happen? C1 is equal to 6 and C2 equal to 2 will be a solution of the system. That is, we have infinitely many solutions for C1 and C2. So, there exist scalars C1, C2, etc. Cn other than the zero solution. This is the zero solution. C1 equal to 0, C2 equal to 0 will obviously be a solution for the system. But other than the zero solution, C1 equal to 3 and C2 equal to 1 is also a solution for the system. C1 equal to 6 and C2 equal to 2 is also a solution for the system. So this system C1 V1 plus C2 V2 plus etc. plus Cn Vn equal to 0 has infinitely many solutions or solutions other than 0. In such a case, we say that V1 and V2 are linearly dependent. Then what do you mean by linearly independent system? The set of vectors is linearly independent if and only if they are not linearly dependent. That is, the only solution for this equation C1 V1 plus C2 V2 plus etc. plus Cn Vn equal to 0 is C1 equal to C2 equal to etc. equal to Cn equal to 0. So from this example, we see that V1 and V2 are not linearly independent. But what if I am considering the vectors V1 is equal to 1, 1 and V2 is equal to say 1, 2. Let us check if they are linearly independent. So again I am considering the equation C1 V1 plus C2 V2 is equal to 0. This implies that C1 times 1 1 plus C2 times 1 2 is equal to 0, which implies that C1 plus C2 is equal to 0 and C1 plus 2C2 is equal to 0. On solving these two equations, I get that C2 must be equal to 0. Substituting C2 equal to 0 in this first equation, we see that C1 must also be equal to 0. So the only solution for this system of equations is C1 equal to 0 and C2 equal to 0. So we can say that the vectors V1 equal to 1 1 and V2 equal to 1 2 are linearly independent vectors. Let us see another example. Is the set 1 2, 3 4 in R2 linearly independent? So we will consider the equation C1 V1 plus C2 V2 is equal to 0. This implies that C1 plus 3C2, 2C1 plus 4C2 equal to 0, 0. So on solving it, we can easily see that this system has a single solution, which is C1 equal to 0 and C2 is equal to 0. So the given set of vectors is linearly independent. Another example, suppose we are considering three vectors in R3, will they be linearly independent? So we have three particular vectors in R3. We are asked to determine whether these vectors are linearly independent. So we have to consider the equation C1, this is my V1, this is my V2 and this is my V3. So we have to consider the equation C1 V1 plus C2 V2 plus C3 V3 is equal to 0. And on solving this equation using Gaussian elimination method, we see that C1 must be equal to minus 2.5 C3 and C2 must be equal to minus 3, where C3 is arbitrary. So if I am giving C3 is equal to 0, C2 will be minus of C3, which is 0, C1 will be also 0. Now if I am giving C3 is equal to 1, C2 is equal to minus 1 will be an answer, and C1 is equal to minus 2.5 into 1 will also be a solution for the system. So C1, C2 and C3 can have infinitely many different values even for this system to have a solution. So this means that other than 0, 0, 0 solution, we have many different solutions for the equation C1 V1 plus C2 V2 plus C3 V3 is equal to 0. Which means that this set of vectors is linearly dependent. Okay. Now these are two questions for you. Determine whether the set of matrices 1 1 0 0, 0 1 0 1, 0 0 1 1, 1 0 1 1 and 1 1 0 1 in M2 by 2 is a linearly independent, and we have another 3 vectors in R3. You have to check whether they are linearly independent. So far we have learned about linear combination of vectors, and the set of all linear combination of a set of vectors is called the span of that set, and we have learned about linearly independent vectors. We are moving on to the main definition of this module, okay, which is called the basis for a vector space. So before moving on to the basis, we must know what a spanning set is. We know what a span of a set of vectors is. Now we are going to learn what a spanning set is. The set of vectors S is a spanning set for a vector space V if every vector in V can be written as a linear combination of the vectors in S. That is, we have already learned what span of a set of vectors is, that is the set of all linear combination of vectors. Suppose I have a set S is equal to set V1, V2, etc. Vn. This set is called a spanning set for V if span of S is equal to V. That is, the set of all linear combination of the elements in S will give me the entire vector space. In such a case, we call S as a spanning set for the vector space V. Example, the set S equal to 1 0, 0 1 is a spanning set for R2, as every vector in R2 must be a linear combination of 1 0 and 0 1. Is it? Yes, because every vector in R2 is of the form AB, where AB can be written as A times 1 0 plus B times 0 1. So as A and B varies, we get all the linear combinations of 1 0 and 0 1. Therefore, we can say that span of this set S is equal to R2. So this set forms a spanning set for R2. And now we move on to the basis for a vector space, which is very important, because a basis for a vector space is a set of vectors that is linearly independent and that spans V. So, if I get a set of vectors V1, V2, etc. Vn, it forms a basis only if they are linearly independent and they span V. So will this set 1 0 and 0 1 be a basis for R2? It will be, because we have already seen that this spans R2. Now all we need to check is whether this set is linearly independent. So how do we check it? Say C1 V1 plus C2 V2 is equal to 0 0 implies C1 plus 0 C2 and 0 C1 plus C2 must be equal to 0 0, which implies that C1 must be equal to 0 and C2 must be equal to 0. So the only solution for the equation C1 V1 plus C2 V2 equal to 0 is C1 equal to Z2 is equal to 0. So this set S equal to 1 0 0 1 is actually a spanning set and is a linearly independent set, which means that this is a basis for R2. Now, the dimension of a vector space is the number of elements in the basis for the vector space. So, what is the dimension of R2? How many elements were there in the basis? What we said is S is equal to set 1 0, sorry, this is 1 0 comma 0 1 is a basis for R2. This set has two elements, 1 0 and 0 1. So, what is the dimension of R2? Dimension of R2 is 2. First example is just the same as what we have discussed so far. Prove that the set S equal to 1 0 comma 0 1 is a basis for R2 considered as column matrices. So in order to prove that a given set is a basis for a vector space, we will have to prove that this given set is linearly independent and that set spans R2. So first we have to prove that span of S is equal to R2. In order to prove that span of S is equal to R2, we will have to prove that every element in R2 can be expressed as a linear combination of the elements in S. So we consider an arbitrary element U is equal to AB in R2. Then suppose we can write AB as D1 V1 plus D2 V2. Then AB will be D1 D2, which means that D1 must be equal to A and D2 must be equal to B, which implies that S spans R2. Now we have already proved the linear independence, that is C1 E1 plus C2 E2 equal to 0 implies C1 equal to C2 equal to 0. Since the given set of vectors is linearly independent and spans R2, the given set is a basis for R2. And what is the dimension of R2 then? The dimension of R2 will be the number of elements in the basis for R2, and here it is 2. Now my question is the basis for a vector space unique? That is, we know that 1 0, 0 1 is a basis for R2. Does there exist any other basis for R2? Does there exist any other set which spans R2 and which is linearly independent? The next question gives an answer for that. So determine whether the set B is equal to 1 1 comma 1 minus 1 is a basis for R2. So what are the things that we have to check? We have to check that this set B is a spanning set for R2 and it is linearly independent. So you can easily check these. B is a spanning set for R2 if there exist scalars D1 and D2 such that AB is equal to D1 into 1 1 plus D2 into 1 minus 1. Solving these, we get D1 equal to A plus B by 2 and D2 is equal to A minus B by 2. So the system has a solution for any choice of scalars A and B. Therefore, B is a spanning set for R2. And we can easily prove the linear independence by solving the equation C1 into 1 1 plus C2 into 1 minus 1 equal to 0. So on solving it, we see that C1 equal to C2 equal to 0. Therefore, the given set of vectors is linearly independent and it spans R2, hence they form a basis for R2. But what is the peculiarity of all the basis elements in R2? Peculiarity is that this is another basis for R2, but this also has only 2 elements. So any basis for R2, the basis for R2 is not unique. In general, for any vector space, a basis is not unique, but the number of elements in the basis will always be the same. That is, for R2, since its dimension is 2, the number of elements in the basis for R2 will always be equal to 2. Now we have to see an extension of the basis which we have seen earlier. This example, this S is actually called the standard basis for R2. This has a name, that is set 10, 0, 1 is actually called the standard basis for R2. An extension of the above example shows that a basis for Rn in general, considered as column vectors, is the set of n tuples E1 equal to 1 0 0 etc, E2 equal to 0 and 0 etc, etc, En is equal to 0 0 etc 1, where Ej has its jth component equal to unity and all other components equal to 0. This set is known as the standard basis for Rn. And how many elements will there be in a standard basis for Rn? E1 has its first entry 0, first entry 1, E2 has its second entry 1, etc. En has its nth entry 1. How many in total how many are there? There are n elements. So dimension of Rn is n. Okay. Now what is the dimension of R3 then? Dimension of R3 will be 3 and the standard basis for R3 will be S is equal to set 1 0 0, 0 1 0, 0 0 1. So this is the standard basis for R3 and we can say that the dimension of R3 is 3. In general, dimension of Rn is n. So we have seen a basis for Rn. Now we will see a basis for M2 by 2. Prove that B is equal to set 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 is a basis for M2 by 2. Again, we have to check whether the given set is a spanning set for M2 by 2. On solving the equation A, B, C, D equal to D1 V1 plus D2 V2 plus D3 V3 plus D4 V4, we get to see that D1 must be equal to A, D2 must be equal to B, D3 must be equal to C, and D4 must be equal to D, which means that there exist scalars D1, D2, D3, D4 such that A, B, C, D is equal to D1 V1 plus D2 V2 plus D3 V3 plus D4 V4. So this set is a spanning set for M2 by 2. The next question is whether the given set is linearly independent. So on solving the equation C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equal to 0, we find that the only solution for this system is C1 equal to C2 equal to C3 equal to C4 equal to 0. So therefore the given set of vectors is linearly independent also. Hence this set B is a basis for M2 by 2. This is again called a standard basis for M2 by 2. And how many elements are there in the basis for M2 by 2? Here there are 4 elements. 1, 2, 3, 4. So the dimension of M2 by 2 is 4. In general, dimension of MP by N, where P by N is, MP by N is a set of all P by N matrices. It will be P into N. Okay. That's written here. An extension of the above shows that the standard basis for MP by N is a set of P into N matrices, each having a single 1 in a different position with all other entries equal to 0. Consequently, dimension of MP by N is equal to P into N. So we will see an example of M2 by 3. Suppose I am considering M2 by 3. Can you give me a basis for M2 by 3? It is very simple. Consider 2 by 3 matrices having a different entry 1 and all the other entries 0. That is, suppose I'll start from 1 here. So 1 0 0 0 0 0. Next 0 1 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 and 0 0 0 0 0 1. This is a basis for M2 by 3. You can easily prove it as we have already proved in the other cases. So this is a basis for M2 by 3, and how many entries are there? 1, 2, 3, 4, 5 and 6 elements are there. So the dimension of M2 by 3 is 6. In general, the dimension of MP by N is P into N. Okay, so that's the end of today's class. Thank you.